Okay. Here we are. We're back again with angled forces, inclined planes. You know what's funny is I tried to upload the last video onto YouTube and it said I've actually hit like a daily upload limit because I uploaded 10 videos. So here we are. This is not actually section 11. This is actually section 12 because I misnumbered it. Okay. Okay. This is just going over some inclined plane stuff. So our first thing here is we have a block of mass m equals 5 kilograms pulled by force 50 newtons at an angle 37 degrees to the horizontal. Determine the normal force on the block and the acceleration if its surface is frictionless. Okay, so no friction. What forces are on here? Well, we've got normal force going up. We've got mg going down, and then we've got this weird friction force right here. Okay. Just called F. Okay, there's no friction, or not friction. Did I say friction force? I meant to say like an applied force. It could be tension. It could be just normal force. Doesn't matter. Okay. The acceleration of the block is moving to the right. Okay, the block is moving to the right. Okay, and the first step here, okay, is to draw your forces. Forces. Okay, make components. Okay, parallel or perpendicular to the acceleration. You want everything to be parallel or perpendicular to the acceleration. So for example, this force right here is not parallel or perpendicular to the acceleration. So instead, we need to take its components and make sure that those components are parallel or perpendicular. This one right here on the bottom is going to be parallel to acceleration because the acceleration goes straight right. Okay, this is F cosine theta. And then this vertical component right here is going to be perpendicular to A, which is perfect, okay? F sine theta. Okay. The next step, so step two is that the perpendicular forces they balance. They should cancel out because what's happening is the perpendicular forces are not affecting the acceleration at all. If the acceleration is going directly to the right, then none of the perpendicular forces can affect it. If they did, then you would not have an acceleration in that direction. Okay. So what's gonna happen is this is gonna be the up forces. The total up forces need to equal the total down forces. So what forces are going up? We've got F sub n, okay, and F sine theta. So I'm going to do F sine theta, okay? Okay, and you set that equal to mg, okay? Okay, we're trying to figure out the normal force on the block, okay? So all that we need to do, okay, um, is do the normal force plus, okay, we've got the F sine theta. F is 50. Sine theta is going to be, so sine of 37 is going to be 3/5. Okay. And then mg, m is 5, and times 10 is going to give us 50. Okay. So you've got that. This should end up being normal force plus, this is going to end up being, it should end up being 30. Okay. Equals 50. So then you should see that the normal force is going to end up being equal to 20 newtons. Okay? Your normal force should be equal to 20 newtons. Now that's just the perpendicular forces. Okay? The parallel forces. Okay? Okay? We need to set those equal to ma. So the sum of the parallel forces needs to come out to ma. Okay, so that's going to be the force that goes that goes with the acceleration is F cosine theta. Nothing is opposing it, so we're just gonna set that directly equal to ma right then and there. Okay, F is going to be is again 50 cosine theta. Cosine 37 is 4/5. Okay, and then we set that equal to ma. Okay, the mass is 5, and the acceleration we don't have yet, right? That's what we're trying to figure out. So then I'm going to do this. This is the part on the left-hand side is going to give me 40, okay, equals 5 times A. And you should be able to see that A from there is going to be 8 meters per second squared. Okay? Pretty cool. Pretty cool. Okay. The next problem is going to look the exact same, except now there's friction. So there's still normal force. there's still mg, there's now, there's this force right here, capital F, and then now you have friction force pulling back, okay? The capital F force still has F cosine theta, F sine theta, okay? And so what you would have to do here, okay, is you would have to take, your perpendicular forces, right? Here's perpendicular, okay? For perpendicular forces, it's again F sub n plus F sine theta equals mg. Now, fun fact, this is not going to change at all because nothing changed in the perpendicular direction. This equation is the exact same as it was up here, and all the values are the same. So normal force is just going to be 20 newtons again. Okay, that's fine. Nothing really changes there. However, the parallel forces, okay, the parallel forces do change because now on top of F cosine theta, there is now an opposing friction force, which is mu Fn, okay, equals ma. Well, now we just plug everything in. This is going to be 50 times 4 over 5, okay, minus mu. We're given mu is 0.5. We're given the normal force is 20, and then we set that equal to ma. Sorry, I shouldn't have put ma. I should have put, instead of m, it should be the 5 kilograms times a. Okay? And this does change your result just a little bit, okay? We already know that 50 times 4/5 is going to give us 40. Okay? Half of 20, 0.5 times 20 is half of 20, so that's just 10, equals 5 times a. Okay, so there's 30 equals 5 times a. And then acceleration should then be equal to 6 meters per second squared. So you see now that having friction decreases our acceleration because our net force is actually decreased. Because now, instead, we now have to subtract that friction force from it. Okay? Okay. Right here, we've got a inclined plane example. Okay, inclined plane example is always fun. So looking at the inclined plane example, okay, we have a block of mass 10 kilograms on a frictionless inclined plane of theta equals 37 degrees. Okay, find the normal force on the block and its acceleration down the page. Okay, or sorry, down the plane. Okay, so if I'm going to draw the forces on it, okay, I'm going to use red for this one. The forces on the block, we've got mg going straight down, okay, and then we've got normal force coming out of the page. Or not, why do I keep saying out of the page? Out of the plane, okay, out of the plane. It literally says it right here, out of the plane. Why do I keep saying out of the page? I'm thinking of magnetism, okay? And then you should know that mg has two components, one that's perpendicular to the plane and one that's parallel to the plane, okay? That perpendicular, so it has an angle right here, theta, which is the same as this angle right here. And that's because of a geometric principle. Okay, that's from geometry. We get that from geometry. Okay. So the part that's perpendicular to the plane is mg cosine theta, and this right here is mg sine theta. Okay. So now, what you should end up getting, okay, is we're going, oh, sorry, the acceleration, I should have clarified. The acceleration is down the plane, okay? The acceleration is down the plane. It tells us that in the problem, okay? So what's perpendicular to the acceleration, okay? Well, what's perpendicular to it, right? Okay, perpendicular, okay? What's perpendicular to the plane? Or to the acceleration? Well, normal force is perpendicular to the acceleration, and so is mg cosine theta. So normal force should be equal to mg cosine theta. Okay, and that's actually important for us to know because, again, the normal force isn't just going to be mg, it's going to be mg cosine theta because it has to directly oppose this part right here, right? The block isn't accelerating down here or up here, so it has to cancel that out. So what I'm going to do is, I don't know what normal force is, but I know what all the other stuff is. Mass is 10. Okay, g is 10. Cosine theta, cosine of 37 is going to be 4/5. Okay, so I get what? 100 times 4/5. Okay, is the normal force, and I should end up getting the normal force is equal to 80 newtons, and that should make sense because 4/5 is 0.8, so times 100 would give you 80. Okay. And then to find the parallel forces, okay, for the parallel forces, then you would do, okay, you got mg sine theta going down the plane. That's it, okay? Mg sine theta down the plane and set that equal to ma, okay? Well, you've got all the values here. This is 10, this is 10, this is 3/5, okay? And this is, the mass is 10, and the acceleration. So then 100 times 3 over 3/5, okay? 100 times 3/5, that's going to give you 60 equals 10a. And you don't need to be a rocket scientist to figure this out, even though I might be one, okay? I don't need to be a rocket scientist to figure this out. A is going to give you 6 meters per second squared, okay? Sounds fun, right? Fun time in physics, right? Fun times in physics. I had a professor in college who would always say fun times in physics, and it's true because it was fun times. Except the last day of that class, it turns out he was going to retire, and he did not say fun times in physics at all. So I was kind of sad. Okay, okay. Here's another example that now the incline has a coefficient of friction. Oh, great! So basically the same thing, but with friction now. Okay. And you'll notice that it changes only a little bit, right? You still have your normal force going up this way. We still have mg going straight down. We still now we have friction force going up this way, okay? And mg still has those same two components, okay? Mg cosine theta and mg sine theta, okay? There you go. Okay? Okay. To find the perpendicular forces, okay, I'm going to use this. I use this upside down T for perpendicular, okay? The forces that are perpendicular to it is just normal force equals mg cosine theta. And guess what? It's the same thing. Nothing changes with the perpendicular forces, okay? Hopefully nothing would change because it's not changing its motion, okay? For the parallel forces, again, I use like the two vertical lines for parallel. It looks kind of like looks kind of like a face, right, where he's just like, okay. But anyways, this ends up being, so now the parallel forces, you have mg sine theta going with the acceleration, which I didn't even draw on here yet. Okay, you have mg sine theta with the acceleration, so it'd be mg sine theta with the acceleration, and from that you have to subtract the friction force, which is mu times normal force, okay, which would be mu, well, I'm going to do mu times normal force, but really it would be mu times mg cosine theta, okay, equals ma. Now, we've already solved for what this is. This is really just mg cosine theta. Mg, so m is, oh shoot, what was the m again? It was what, 10? I think it was 10 from the last part. Yeah, it's 10, okay? 10 times 10 times the sine of theta, okay? This is going to be sine of 37, which is going to be 3/5. That part's unchanged. Subtract from that the mu, which is 0.5, times the mass, which is 10. Or actually, I don't even need to do all that because I already figured out what mg cosine theta is. It's 80. Okay? It's 80. Okay, I already figured that out. I figured that out from right here. Okay? And then the mass is 10 and the acceleration. Okay? Okay, so then I calculate that out. This whole left-hand side right here, okay, mg sine theta, that's going to give us 30, okay, just like I got before. Sorry, no, 60. Sorry, 60. What was I thinking? I was thinking, still in the mindset of using 50. This is going to give us 60, okay? 60 minus half of 80 is going to be 40 equals 10 times A. Well, you should notice, okay, let me put the 10 in parentheses so you can actually see that. This is going to give us 20 right here equals 10 times A, and that should give us an A of 2 meters per second squared. Wow, what a trek that was, okay? What a journey. All right, well, that was inclined planes, all right? Live, laugh, lab, okay?